Have you ever wondered how you could possibly map out a huge, complex network by just following one single path at a time? And do it without getting lost while still guaranteeing you hit every single spot? Well, that is the incredible power of depth-first search. I mean, think about it. If I dropped you at the entrance to a giant maze right now, what's your gut instinct? What's your strategy? Do you try to peek down every single path right from the start? Or do you commit? Do you pick a path and just go? Right. You pick one way and you follow it as deep as it'll possibly take you. And when you hit a dead end, what do? You backtrack, you walk back to the last place you had a choice, and you try the next path. That simple human intuition, well, that's the beating heart of depth-first search. Okay, so here's our game plan. First, we're going to really nail down the core idea. Then we'll get into the mechanics of how it actually goes deep and backtracks. From there, we'll talk about code and its true cost. Performance. Then the fun part, the DFS toolkit, all the cool stuff you can do with it. And finally, we'll answer the big question, when do you use DFS? So, let's get into it and give our maze-solving strategy its proper name. At its core, depth-first search, or DFS, is an algorithm for walking through a network, what we call a graph or a tree. And you know what? The name tells you everything you need to know. It goes for depth first. It's relentless. It commits to one single branch and explores it to the bitter end before it even considers trying another one. Okay, so this whole go deep, then backtrack thing sounds great, but how does a computer do it without getting confused? Let's break down the mechanics. It's actually a pretty disciplined little dance. You start somewhere, let's call it node A, and you immediately mark it visited so you don't come back by accident. Then you look at its neighbors and pick one that's unvisited, say node B. Now you're at B, and you do the exact same thing. Find an unvisited neighbor, C, and dive again. You just keep diving deeper and deeper until, bam, you hit a dead end, a node with nowhere new to go. Only then do you backtrack. You go back to the last spot that had another choice you didn't take, and you start exploring from there. It's this simple, repeated process that guarantees you cover everything. Now, when you go to code this up, you have two main flavors. The recursive way is beautiful, it's elegant. The code is often super clean because the programming language's own call stack remembers the path for you. But there's a danger. If your graph is incredibly deep, you can literally run out of memory on that call stack and your program crashes. That's a Stack Overflow. The other way is iterative. Here, you manage the backtracking yourself with a data structure called a stack. It's a bit more code, but it's safer and gives you way more control, especially for massive real-world problems. All right, let's talk about the bottom line, the stuff that really matters in an interview or when your application is slowing down. What's the true cost of running DFS? This right here, this is the magic number for DFS, OV plus E. V is for vertices, the nodes or points, and E is for edges, the connections between them. So what does this actually mean? It means the runtime of the algorithm grows in direct proportion to the size of the graph. That's it. It's because a good DFS implementation is incredibly efficient. It visits every single vertex and every single edge exactly one time. No wasted effort. But, and this is a big but, you only get that amazing O of E speed if you store your graph the right way. If you use what's called an adjacency list, where each node just keeps a list of its direct neighbors, you're golden. But if you use an adjacency matrix, a big grid, you have to scan a whole row just to find a node's neighbors. That slows everything down to O of E squared. On a big graph, that's the difference between an answer in milliseconds versus waiting all afternoon. This is a classic interview question, so remember it. The data structure matters a lot. And what about memory usage? Well, the space it needs is O of V. Basically, you need enough memory to keep track of all the vertices you've already visited, plus enough room for the stack itself. In a worst-case scenario, like a graph that's just one long single-file line, that stack might have to hold every single vertex. Okay, so we get how it works, and we know what it costs. But so what? I mean, what can you actually do with this thing? What problems does it solve? Oh, this is where it gets really cool. DFS isn't just a way to walk around a graph. It's a fundamental building block for solving tons of other problems. You want to know if your project dependencies have a circular reference that'll break the build? DFS does cycle detection. Need to figure out the right order to do a bunch of tasks that depend on each other? That's called topological sorting, a classic DFS application. It can find clusters in social networks, identify critical single points of failure, and yeah, of course, it can solve mazes. And hey, don't just take my word for it. Way back in 1972, the legendary computer scientist Robert Tarjan pointed out that DFS is the fundamental primitive that makes solving all these other complex problems not just possible, but incredibly fast. Mastering DFS is like learning a power chord in music. Once you know it, you can suddenly play 1,000 different songs.
This leads us to the final and maybe most important question you'll face as a programmer. When do I pick DFS, and when do I use its equally famous cousin, breadth-first search?
Let's just boil it down. DFS goes deep. BFS goes wide, exploring level by level. DFS uses a stack, BFS uses a queue. But here is the #1 most important takeaway. If a problem asks for the shortest path between 2 points on a simple graph, the answer is always BFS, period. DFS just finds a path. It makes absolutely no promises that it's the fastest one. On the flip side, DFS can sometimes be lighter on memory if you're dealing with a really wide, bushy graph, because it only has to remember one path at a time. So here's your cheat sheet for your next technical interview. Remember, DFS goes deep. BFS goes wide. DFS uses a stack, which is last in, first out. BFS uses a queue, which is first in, first out. If you see the words shortest path, your brain should just light up with BFS. Their time complexity is the same, so that's not the differentiator, and make sure you're comfortable talking about both the recursive and the iterative ways to implement DFS. At the end of the day, depth-first search is more than just an algorithm. It's a strategy. It's a way of thinking, of diving headfirst into a complex problem and methodically exploring every possibility until you find a solution. It's a fundamental tool for exploring the unknown. So the real question is, what problems are you going to solve with it?